Hi boys, I'm starting chapter 11 and we don't do all of the chapters in or all of the sections in chapter 11. And I also want to point out that I am skipping the one section that we do in chapter 10 right now. And the reason for that is I believe it might be a little bit easier to solve those questions when we have the knowledge of what a radical expression looks like. Now, when we're talking about all of these radical expressions, we're talking about the square roots of different numbers. One thing that we need to know about before we simplify them is that there can be no perfect square factors other than one within the radicand. And radicand is just talking about that symbol. There can be no fractions, and there can also be no radicals in the denominator of a fraction. And we'll address those as they come throughout the lessons. And I broke this lesson up into more than one video. So for today, we're just going to focus on how to simplify these radical expressions. And we're going to be utilizing something called the product property to just be the underlying reason as to why we are allowed to do the math that we set up. What this product property states is that, let's say A and B are two different terms. I'm allowed to break them up through multiplication and still say this same expression is equal. The radical A times radical B. It's still equal to the radical of A and B together. Same thing with 40. If I want to think of any two factors of 40 through multiplication, I can say the radical of 40 or 4 times the radical or square root of 10 is still equal to the square root of 40. And we're going to practice how can we get to the simplified answer. If you don't print out these notes, and I will post them, I suggest writing down these few examples of perfect squares that I just expect you to know quickly. Should you know a little bit more? Yes. For example, 11 times 11, 12 times 12, 13 times 13, possibly 14 times 14. But since you do have a calculator, that can be a heavy reliance for you on understanding the different square roots and perfect squares. So I'm going to move over to this slide to show you the examples that I have written in your notes. I show the work a little bit differently than your textbook. I kind of use like a little like factor tree type of deal when it comes to factoring down these specific questions. Now the goal is to think of factors of these numbers that are a perfect square. And when you find a perfect square factor, you're able to get rid of that radical symbol. And we want to break down these numbers as simply as possible. So when I'm looking at the number 72, there's a bunch of factors that go into that. 1 and 72, 2 and 36. Now I'm going to stop there because if we look back to the notes sheet, isn't 36 a perfect square? You want the biggest perfect square to make the simplification process easier. And I will show you, if you didn't come up with 36 at first, that it is still possible to simplify these questions. So if I wanted to simplify 72 by using our product property of multiplying the square root of 2 times the square root of 36. Because again, if we multiply those two together, they're still equal to 72. Is the square root of 2 a perfect square? No, because no number times itself will equal 2. But is the square root of 36 a perfect square? Yes, because 6 times 6 is 36. So to simplify this and have our final answer, we take out this perfect square, which is 6. So there's no radical anymore. And then we write next to it the radical of 2. So 6 radical 2 is simplifying the square root of 72. Now, if you did not pick up on 2 and 36, I'm going to erase this so to show you how it could have been done a different way. You could have done, let's think, maybe 8 and 9. Oops. Now, one thing I noticed is 8 can be broken down even further because 8 still has factors that go into it other than 1. So I can still break down this square root of 8 and get the square root of 4 and the square root of 2. And you want to keep breaking things down to just check to see if there's a perfect square factor within the smaller numbers. So if I look, I broke this down just like when you're used to making factor trees in lower grade levels. I have 4 and 2. Is 4 a perfect square? Yes. So I'm allowed to take out a 2. And is the square root of 2 a perfect square? No. And I'm leaving a little space because now I want to deal with the square root of 9. Is that a perfect square? Yes, the square root of 9 is 3. So when you take out two different perfect squares, you multiply them together on the outside of the radical. And we're going to have 2 times 3 is 6, times the square root of 2. So notice we still have the exact same answer anyways. In the next few examples, we want to think of 42 and 2. And once again, if we think of 1 and 42, 2 and 21, we're really not getting towards a perfect square yet, which is okay. We're allowed to pick any numbers that we want. So if I wanted to think of maybe, let's say, let's use 2 and 21. Can I break down either of these further? Yes, I can continue to break down 21, and I can have 7 and 3. But are any of these numbers repeating, or are any of them perfect squares? No. So that means I can't break this down any further. The square root of 42 is already simplified, and there's nothing else you can do. So that would be your final answer. Moving on to another example. If I wanted to take the square root of a number as well as a common or a variable, I want to break down the number first. So let's think of 2 factors of 18. And I'm going to choose 3 times 6. Now neither 3 or 6 are perfect squares, but I can continue to break down 6 and get the square root of 2 times the square root of 3. Once again, neither of them are perfect squares. However, notice that I have 2 radicals of 3. So that means I'm allowed to take this number 3 out of the radical and just be left with a 3 because there's a pair of them. And whenever that happens, you are allowed to take that out. And then we're just left with 3 radical 2. Now to deal with y, I want to think of, well, what can I multiply y by itself to get y squared? And I know that if I take the square root of y times the square root of, y times y, that is equal to y squared. So once again, I have a pair. I can take one of those out, and now I can rewrite this as 3y radical 2. And that is our final answer. Now some of you might be saying, well, why couldn't I multiply this and get 9 times 2? You could have, and I will show you what that looks like. You could have started this whole thing out, and we'll leave the y's because there's nothing else you can do with that. And we're going to see what happens if you chose from the beginning the square root of 2 times the square root of 9. I noticed that 9 is a perfect square. What's the square root of 9? 3. And then radical 2 comes down again, and our y's stay the same. So there is more than one way to get to the answer. For the last example, we're going to be doing just variables. So we want to think, what could I have multiplied to get y third together? I could have said y times y squared. And then if I break this one down even further, or I just know that any variable risen to the second power is a perfect square, I'm allowed to take out a y for my final answer, and I'm definitely going to be left with the square root of y. And then if I look at z to the 4th, I could have taken out a z squared, let's use a different color, z squared, and another z squared. Because remember, when we multiply the same base, we add the exponents. So 2 plus 2 is 4. And look at that. It's a pair of radicals. So I can take them out and have y times z squared with a radical y left over. I also know that 4 is a perfect square. So if I took the square root of 4, I'm left with z squared. I will post another video of more examples if this was still not too helpful for you. But at this point, if you feel comfortable, you don't have to watch both videos.